So automation is what, in my opinion, changes this kind of formal techniques from being a burden to something that can actually be helpful for developers also beyond what the law requires from them.
Thank you for watching this video. Please help us keep the show alive by liking and sharing this video, and by subscribing to the show and making sure the notification button is switched on. For those of you who can help a little bit more, there's a Patreon link down below where you can contribute whatever you can. Every little does help, and all the money will go directly back into the show. You can also keep up with our latest content on Instagram at The No Show Pod, as you can see on the screen. As you know, The No Show is an initiative designed to make academic research accessible to everyone. So do contribute to the conversation, leave some questions, have a discussion, and I'll make sure I get back to everyone. Carsten, thank you so much for joining me on The No Show. I'm really pleased to have you.
Thank you very much. I'm very pleased that you're having me.
Excellent. One of the things that, before we sort of get into your research and the details of it and sort of the, one of the things that really caught my attention about your research was the fact that it is in many ways diverse, but it is still it focuses on a sort of broad range of problems in sort of computer science. So why is it that you sort of, are you sort of inquisitive in the sense of constantly wanting to find new problems to solve, or is it just sort of how you've ended up in research?
I would say that I am inquisitive in that being a researcher involves learning constantly, also learning about problems that others have. And then often enough, it turns out that one can transfer solutions from one problem to the other, which then can lead to further progress. So this cross-pollination between different problems is a very important aspect of research, I find.
Before we started this recording, and this is why I say what I say and why I find your research super interesting, is because you've looked at sort of ways to measure costs of running a program, and you've essentially created a program that does your marking for you. So it's incredible that you have these sort of diverse areas. And I want to get into them a little bit more, but before I do, how did you sort of find yourself becoming a researcher in computer science?
Originally, I studied computer science at Aachen University in Germany with a 1-year exchange year in Valencia. And after I returned from Valencia, I was looking into what am I going to do my final project in my integrated master's about. And there were several areas that caught my interest, but one in particular was this area of automated program verification, because it combines diverse activities. There is theoretical computer science in there, so the mathematical aspect. There is writing computer programs for the automation, so there is a strong component also, not just talking about it, but actually doing it, making it work. And finally, the experiments also allow me to see whether it actually makes a difference, whether it really works.
And what were the outcomes of that initial project that you did?
The outcomes, so in that master's project, my task was essentially to provide a new method for finding such proof certificates. So we talked about the cost of running a program, one can relax this question, just say, will the program always give me an answer for every input? And or will it just get the system stuck if we ask it the wrong question? And to find an automatically a certificate, a proof, by now the standard approach is we provide, there is a template for a certificate, but that template has holes that need to be filled in. And the outcome was I used a technique called satisfiability solving, so a form of constraint solving. One could call it declarative programming as well. So I described what should the entries for the holes in the certificate look like. Then I asked an external tool, find me a solution for that. The external tool knew nothing about program analysis or verification, but it knew how to find solutions for such questions.
So, I mean, that's incredible that, a program that doesn't typically do that is sort of like trained essentially to find the answer or fill in the holes. So if you were to put that into context, and if we look at it as a bigger picture, where does this program or this sort of this, I guess, process, where does it become useful in industry or in just life in general?
So the main goal of this research is to improve the quality of software, to make it easier for software developers to ensure that their program does what it's supposed to do. Be it in having the right output or in always providing an answer with suitably little cost. And this matters already a lot in some areas of life. So software that is run on an airplane, for example, to steer an airplane, there are laws that require the constructors of the airplanes to get a certification by safety experts that their software is safe and a crash of the software won't lead to a crash of the airplane, to put it like that. And one thing, recently I attended a lecture about the more wider uses of software in society. So we're all probably pretty used to seeing having a click-through terms of use, which say this software is essentially good for nothing, and you are using it at your own risk. So that may be acceptable for, I don't know, a word processor, where if it crashes, it's not the end of the world. But if the system has more importance for the daily life of people, if people depend on it, it would be good if we had stronger guarantees. And the trend is going towards more legislation that sets the bar a bit higher.
And this is all incredibly, useful things, and I suppose naturally it would, like when you say it improves the quality of programs, naturally it would it improve the cost of running a program over time?
So it would improve essentially the quality and the cost. Well, the fewer errors a program has from the start, the less needs to be paid for then repairing the errors or for the outcome, the accidental side effects of the errors. So our goal is to make it as easy as possible for software developers to benefit from this research without having to learn all the techniques in that research. So they're not, if we tell a software developer, here's a description how you can show that your program really works correctly, you must use pen and paper and it will take you a month. They won't do it. But if we give them a tool and the tool answers in a minute, that gets used.
There's an interesting facet to this, because at the beginning you said, or sort of rather prior to recording, you said the research that you did sort of measures the cost of running a program without actually running it. And you mentioned that, you look at the cost of time, you look at the cost of, network traffic. And the one that caught my attention was the cost of energy. Now, this is incredibly interesting, especially in this day and age, when you have, energy consumption becoming a headlining factor and in relation to carbon footprint and that sort of stuff. How can, I suppose, would predicting energy consumption, can it be applied to something like, for instance, the blockchain, and figuring out how much energy it's going to run? Or is it really specific to sort of niche, like a specific software?
The techniques are generally applicable. Applying it to specific programming languages is a different question. So that is essentially something where industry takes over from researchers and builds tools that really support all the different details of a programming language, not just the core features. And I like that you mentioned blockchain, because for Ethereum, so one of the coming or currently used blockchains with automatically checked contracts, they have the restriction that checking the contract may only take a certain number of steps, and there is research to automate this check so that the checking doesn't accidentally run out of gas, so to speak.
Okay, and I can see the picture here. So essentially the key technology here is this automatic checking.
Yes, so automation is what, in my opinion, changes this kind of formal techniques from being a burden to something that can actually be helpful for developers also beyond what the law requires from them.
That's very interesting. You did this really sort of interesting research, or sort of developed a really interesting algorithm, because as academics you sort of have faced the dilemma of having to like go through hundreds of students per week, and checking their code, especially computer science students, and checking their code and the programs that they write. Now you came up with this, you and your colleagues came up with this really interesting tool that essentially uses the same technique that we've been discussing to check that. What does it check actually?
It checks, so given two programs where the idea is one is the program that the teacher wrote and the second program is one that the student wrote. Our analysis program checks if for all possible inputs, the two programs will have the same output. So here program isn't about a full application, but rather just a small piece of an application, a small function as it's called. And such a function takes some values as an input, so data values, and will do some computations with it and return a result. How the computations work internally, that can vary from there are many ways to come up with the same answers, and checking automatically, so checking by hand that they come up with the same answer is, well, essentially one just has to look long enough at the programs to see that they do the right job. And it would be, of course, nicer to have a computer check this with techniques that are always correct, and not just if, let's say, the teacher has drunk enough coffee.
And I mean, what's incredible about this bit of research is that you took, a check that would typically take, I don't know, like several hours to be done by a human being. It now takes how long?
It's overall a minute, let's say, for a number of student programs.
So essentially, I mean, this is incredible for academics in general, who over the past decade have found themselves in a difficult position, given that their time for teaching and research has been diminished because of all the admin and all that sort of stuff. And this is essentially part of the admin that you're eradicating such a significant portion of it. Um, has this been taken up with a keen interest from um, academics and computer science teachers, or is it still very new?
It's still relatively new. So, and I should also mention limitations of this research. Namely, one limitation is it doesn't always give an answer. It will, if it gives an answer and says, yes, these two programs always have the same output, then we can believe that, unless we've made a mistake in writing our own program. Or it might say, no, these two programs, one input so-and-so, they have different results. But there is a third option. Our analysis tool is allowed to say, oh, don't know. And the reason is not that we haven't fully understood the program. That's a very fundamental limitation in program analysis and verification. That's based on an old theoretical result going back all the way to Alan Turing. The result says essentially we can't even check automatically if a given program will always stop for all inputs.
Mm-hmm. And I mean, there's, as I said earlier on, you have a really sort of a diverse set of learnings, and you say because the solutions tend to be transferable. Where next would you look to sort of use these solutions?
Currently, I'm working with collaborators in France, in Lyon, on looking into how can we use these observations from cost analysis to be able to automatically parallelize programs. So, well, what do I mean by that? These days, when we buy a new computer, it doesn't just have one computing core, but it's often between 2 and 8 computing cores, and tendency is rising. The problem is they can't make them much faster because they get too hot. And there are also other physical limitations, but they can put in more computing cores. The problem now is programmers normally write programs that run on a single computing core, but we would like to be able to use them all, not just one of them.
Mm-hmm.
And writing programs that work correctly with several computing cores as a programmer is hard. What we would like to do is programmers don't have to relearn, but rather we have better tools that will translate such a program to machine code that will run on several, so that will really use all the capabilities of the new computers that have several computing cores.
Well, so as of now, how you mentioned that they can't use them all at once. So as of now, how does it work?
In practice, the several computing cores are being used. Let's say if different programs, each of them can use one on its own. So maybe if you have one program running to watch a YouTube video in the web browser, then in parallel a video is being converted to a different program. That will happen on different computing cores, and you get a benefit from having a new computer. But if you want to benefit inside a single program, then that single program needs to be specially written to use the several computing cores.
Mm-hmm. And what does that mean for the average consumer to be able to use all these computing cores at once?
Essentially, it means if programs can use the several computing cores, the consumers benefit by they don't have to wait so long for the program to get back to them with an answer. It will depend on the problem at hand. So for watching a YouTube video, it suffices to have, one doesn't need the newest computer. But if there are applications like transforming a video to a different format, those could get a noticeable speed up.
Mm-hmm. And so fundamentally, it's speed. But then if we look at how that would benefit industry in general, is it just the same thing? Is it speed, or can that then be translated into further benefits, second layer benefits or third layer benefits?
So other benefits include in energy. So energy consumption
Mm-hmm.
is you mentioned this earlier. It matters on several levels. It matters for the consumer who on their mobile phone doesn't want the battery to run out so quickly. And it also matters for big industry with their data centers. If they can make their programs a little bit efficient, and they are running on millions of computers, for each single computer, it just means a tiny bit of energy. But multiply that by 1,000,000 and, well, you save money, energy, and thereby money.
That's that. I mean, that is really, really fascinating. Where can people find you online at the moment?
So the results of my research, well, it's available online on my webpage. So the papers are available for public downloads in the form of preprints. Then the resulting tools, the software tools, the audience would probably be software developers, are available for download for them, so they can try to apply them and possibly get back to us with feedback. And well, there are of course now the podcast summaries about 2 selected papers.
Absolutely, and we'd. I mean, I'll link all the if you can share with me the GitHub and your webpage.
With pleasure.
I'll link those onto the episode so that the listeners can get direct access to it. Finally, before we sort of wrap up, I want to ask you, what kind of advice would you give to any developer or anyone studying computer science that wants to get into this field that that you're researching and look at the same technologies?
So advice that I would give is it's to enter this, it is good to be a bit of an all-rounder. So to both be comfortable with the theoretical side and also with the programming side. So over the years, I have found that a number of students are comfortable just with one of the two sides of the area, the theoretical, or they're good programmers. But what is needed to drive this area further is to have a combination of the two.
That's and I think that's spot on, because I mean, just typically as students, you shy away from things that you're not really, you don't feel good at. So I think you hit the nail on the head. Carsten, thank you so much for joining me. I've really enjoyed this discussion, and I really hope to have you on once you've made some more developments, because I think this stuff is incredibly important, and our audience would love to hear it.
Thank you very much, Hussein.
Thank you for watching this video. Please help us keep the show alive by liking and sharing this video, and by subscribing to the show and making sure the notification button is switched on. For those of you who can help a little bit more, there's a Patreon link down below where you can contribute whatever you can. Every little does help, and all the money will go directly back into the show. You can also keep up with our latest content on Instagram at The No Show Pod, as you can see on the screen. As you know, The No Show is an initiative designed to make academic research accessible to everyone. So do contribute to the conversation, leave some questions, have a discussion, and I'll make sure I get back to everyone.